Billions in cutting-edge cameras aimed at a once-in-a-lifetime interstellar visitor. The images arrive, and the world sees a fuzzy white dot. Expectations explode, trust trembles, and the clock starts as the sun prepares to hide our only witness. Stay with me. 72 hours ago, the European Space Agency published what they called the closest view yet of the interstellar object that has gripped the world. The release followed months of careful build-up. Mission updates, orbit projections, promises of clarity. 7 orbiters around Mars were in position to try for a historic catch. This was marketed as the shot of a lifetime. Then the first pictures dropped. A pale smudge creeping across a starfield. No crisp nucleus. No obvious structure. Just a blur that looked like someone had breathed on the lens. You felt that lurch in your stomach. I did too. How can billions in hardware produce something that looks worse than a backyard telescope on a good night? Social media did not wait. Side-by-side posts compared a sharp amateur image of a known comet with the new release from deep space. The conclusion felt obvious. The professionals failed. The amateurs won. Outrage traveled faster than context. Before we jump to verdicts, take a breath. What if this was never a fair fight? The European camera that produced the images was built to map bright Martian terrain from just a few hundred kilometers up. It was not built to resolve a faint object tens of millions of kilometers away. Angular resolution is the real boss here. When you convert microradians per pixel to kilometers per pixel at that distance, the math tells a blunt story. The estimated nucleus of the visitor is far smaller than a single pixel. You cannot pull structure out of photons that never hit the detector. That sounds like a convenient excuse until you run the numbers yourself. At around 30 million kilometers distance, the stated resolution translates to roughly hundreds of kilometers per pixel. The best-case nucleus estimate is a handful of kilometers to a few dozen. That means the solid core would occupy a fraction of 1 pixel. Tell me, how do you photograph the shape of something that does not even fill a pixel? You do not. You see a point source drowning in a glow from gas and dust, and the point spreads under the instrument optics. The result is a dot, so why release it at all? Because public curiosity is not a spreadsheet. People wanted something. Agencies knew the limitation, yet the world had been primed. If you say nothing, suspicion blooms. If you share what you have, disappointment blooms. In that no-win space, a fuzzy dot can act as a release valve. It gives the public a placeholder to argue over, while higher resolution teams process their data. That is not a scandal. It is a communication strategy born in a pressure cooker. Here is where the story starts to bend. Even as the dot made the rounds, silence thickened in places that usually speak. The most powerful imager at Mars did not publish frames. Other orbiters with decent cameras did not either. The stated reason from one side of the ocean was a government shutdown that froze normal outreach. That might explain one channel, but it does not explain them all. Meanwhile, the sky added a complication. Within days, the visitor would slide behind the sun from Earth's point of view. The most active moment would happen while our best ground-based telescopes were blinded by glare. You can feel the tension in that timing. Hype, then blur, then quiet, then a looming blind window. Is that all coincidence, or is something else going on? The honest answer is that mission pipelines are slow, and the sun is not on our schedule, yet perception matters. When the public feels shut out, stories rush in to fill the empty space. That is when we need clear rules for what counts as evidence and what counts as a question. Here is what we know so far. We have a confirmed interstellar object on a path that carried it near Mars. We have at least one set of images from a camera that was not designed for this job. Those images look poor because the physics of resolution made them poor. We have other assets that should beat that performance, but they have not released anything yet. We also have a real calendar constraint, because the sun will hide the visitor during the days when heating could make it most dramatic. Each of those facts is checkable. Each is enough to create heat online even without a grand conspiracy. So what happens next? If this were only a story about optics, we could stop here. It is not. The dot did not end the conversation. It pulled in a wave of amateur observations, some sharp, some over-processed, and those fed a second fight about what counts as seeing. It pulled in a set of claims about chemistry, heat, and motion that would be extraordinary if confirmed. It even pulled in a half-century ghost called the wow signal, and a geometry that seems almost too neat. That is our path through the noise. We will hold the verified numbers tight, We will mark our speculation clearly, and we will keep our questions sharp enough to test. We are going to walk the line between excitement and care. You deserve energy, you also deserve precision. If that balance sounds right, stay with me. The next piece is about expectations and optics, and why some images were always going to disappoint no matter how much we wanted them to sing. You and I were promised a reveal. What we got looked like a smudge. The quickest way to decide if that was a failure or a foregone conclusion is to run the optics in plain language. Once you do, the picture stops being an outrage and starts being a math lesson that anyone can check. The European orbiter camera that released the viral frames was designed to shoot Mars from close range. It maps bright terrain a few hundred kilometers below the spacecraft. Its pixels capture angles, not sizes, and the number that matters is angular resolution. The instrument specification is about 11.36 microradians per pixel. That sounds abstract until you multiply by distance, put the target roughly 30 million kilometers away. Each pixel then spans on the order of 340 kilometers. Now compare that to the estimated size of the solid nucleus, somewhere between 5 and 46 kilometers across. The core would fill a small fraction of 1 pixel. You cannot resolve shape that does not occupy even a full pixel. You capture a point source. A point source spreads light inside the optics and becomes a fuzzy spot. That is the point spread function at work. It is not scandal. It is physics. Brightness piles on. The camera is tuned for Mars, which is sunlit and high contrast. The interstellar object is faint. The principal investigator said the target was thousands to hundreds of thousands of times dimmer than normal scenes. Dim objects demand longer exposures or more frames to stack, but a long exposure can smear a fast mover, and stacking can only help if the signal is strong enough to begin with. When signal to noise is poor, enhancements mostly enhance noise. You can raise the contrast and sharpen the blur, but you are painting pixels with guesses, not discovering hidden edges. Think about it this way. You stand on a beach and try to photograph a walnut sitting on a distant ship over the horizon. You can buy the best phone on the market. You can pinch to zoom until your fingers ache. You will not see the walnut. The optical limits are not insults to your effort. They are the rules of the game. A camera optimized for dunes at 10 meters is not the camera for a walnut across the ocean. So why build hope for a detailed view? Part of that is the way we talk about missions. We say closest, and the mind hears clearest. We say aligned fleet, and the mind hears cinematic coverage. There is also a real communication dilemma. If an agency warns for months that the first images will be underwhelming, few people will listen. If an agency says nothing until it can release something better, people call that secrecy. When the moment arrives and curiosity peaks, a team can either share what the instrument truly saw, which is a dot, or hold back and fuel suspicion. Sharing the dot is the less harmful choice, as long as you tell people why it is a dot. There is one more nuance. A blur hides structure, yet the diffuse glow still contains information. Astrophysicists can measure brightness, color, and how the dot moves across the background. Those numbers feed models of dust and gas behavior. You cannot sketch the nucleus from such data, but you can estimate activity and constrain size. That kind of science is quiet. It does not light up feeds. It matters. Here is our quick reorientation. We are separating physics from perception, so we can keep our questions sharp. What do the tools allow? What do the numbers prove? Where is speculation trying to sneak in? If we keep that thread in hand, the rest of the story stays honest even when it gets dramatic. The equation changes when you point a very different camera. Around Mars, there is a famously sharp eye that can see objects on the ground, the size of a table. From orbit, that is astonishing performance. At the much larger distance to the visitor during the flyby, its pixels still translate to tens of kilometers rather than hundreds. That is enough to begin testing for extended structure in the coma and to set much tighter limits on nucleus size. It does not guarantee a poster image. It does promise a better constraint on reality. Which brings us to the part everyone is waiting on. Where are those frames? Before we go there, one last point about the European release. Engineers knew the limitations. They took the shot anyway because sometimes you try even when chance is slim. They released the result because the world was watching and because even poor frames add a datum to the record. That choice makes sense if you care about public trust. Trust does not require gloss. It requires context. The missing piece is not that the dot was shared. The missing piece is the public expectation that the next cameras should be able to do much better. That expectation is reasonable. If this kind of clear explanation helps you make sense of the noise, keep watching and bring a friend who loves space puzzles. We are moving to the system that could have pierced the blur and why it did not speak when people expected it to. The answer will say a lot about how science and institutions work under pressure and why silence can feel louder than 1,000 blurry pixels. There is a camera at Mars that changes the game. High-resolution imaging science experiment rides on the Mars Reconnaissance Orbiter, and it is famous for doing something that sounds impossible. From orbit, it can pick out features on the ground the size of a kitchen table. When people heard that, they expected a sharp look at the interstellar visitor. Instead, they heard nothing. The silence hit harder because of what the math promised. At the distance of the object during the flyby, high-resolution imaging science experiment would have worked at something like tens of kilometers per pixel rather than hundreds. That is far from a portrait, but it is enough to measure whether the light is truly point-like or has a measurable spread that hints at structure. It is enough to tighten the upper bound on nucleus size by a real factor. So, why the quiet? The official reason from the United States side was a government shutdown that put most outreach and public-facing updates on hold. Websites stopped updating, social media managers were furloughed. Pipelines that carry data from instrument teams to public portals slowed to a crawl. That does not mean scientists stopped working. It means their normal voice to the outside world went soft. There is another part to the story. Other nations were not bound by that. Shut down. China had an orbiter in position to watch. The United Arab Emirates had an orbiter with a moderate resolution camera and a clear view. Europe had already shown its dot and could have added context. Yet they were quiet too. Separate agencies and separate priorities arrived at the same outcome at the same time. That pattern is hard to ignore without leaping to claims that go beyond evidence. We do not need a secret agreement to explain it. Imaging a faint, fast object is a delicate job. Teams must point, track, calibrate, and then confirm that what they caught is actually what they think it is. Releasing a frame that contains a processing artifact would wound credibility. Waiting for careful checks is the opposite of hiding. It is caution. Inside mission teams, the path from raw pixels to public release is not a straight pipe. Telemetry must be decoded. Instrument quirks are removed. Geometry is verified. Stars in the background are matched to catalogs to lock down pointing. Only then can a group speak in numbers with confidence. Add a workplace shutdown for the largest agency in the chain, and the cadence slows further. Still, perception matters. The public saw a timeline that felt theatrical. First the blur that set everyone buzzing, then a sudden quiet from the camera that could help. Finally, the calendar twist as the object rushed toward a period when the sun would hide it from view. That sequence turns a normal calibration delay into a cliffhanger. People fill the gaps with stories because the sky refuses to answer on command. We are pairing urgency with discipline. We do not confuse a communication freeze with a data void. We keep asking what the best cameras should be able to show and what they must check before they show it. That keeps our questions pointed at the right doors. There is also a technical reason to expect that the best frames might not look dramatic even when they arrive. At tens of kilometers per pixel, a small nucleus is still, smaller than a pixel. What changes is the shape of the light profile and the way it falls off with radius. That profile can reveal whether we are looking at a normal coma or something that adds edges where there should be smooth haze. It is a subtle kind of seeing, yet it matters. While the big instrument stayed quiet, the internet did what the internet always does. Skilled amateurs and curious newcomers tried to fill the silence. Some used standard stacking and careful calibration. Others pushed AI enhancers that can turn noise into art. A few results looked intriguing. Many looked cinematic. The good and the fake flowed together in the same feed, which made patience feel like weakness, even when it was wisdom. This is the moment when the center of gravity in a story begins to shift. Institutional cameras move on their own timelines. The crowd moves on emotion and novelty. If you are trying to discover what is real, you have to hold two ideas at once. Institutions can be slow and also careful. Crowds can be energetic and also wrong. The truth does not owe either side quick delivery. We will ask again for the frames from the sharpest eye at Mars. We will read the documentation when it arrives and look for the details that settle questions instead of stirring new ones. Until then, we keep our attention on what can be checked today. That means looking closely at the amateur claims, sorting the signal from the stylized, and seeing what survives contact with basic physics. That will lead us directly into the viral backyard image that kicked off a new wave of debate and the deeper question it raised. When a credible observer shows an angular form inside a haze, what are we actually seeing? An experienced Portuguese amateur posted a processed frame that showed something no one expected. Inside the faint halo, there seemed to be angles, not a soft snowball, not a watercolor smear. Sharp-looking edges hinted at panels or veins. The picture lit up the internet in hours. So what are we actually seeing? Start with the gear. The observer used a solar telescope that is spectacular at taming the brutal light of the Sunday. That instrument carries narrow filters and optics tuned for bright targets. The interstellar visitor is a faint source against a dark sky. That means the hardware is operating far outside its comfort zone. It can capture photons, yes. It can also imprint quirks that are harmless when aimed at the sun and misleading when aimed at a dim smudge. Now follow the pipeline. The raw frames were stacked to raise the signal. Stacking is standard. Align many images, average out noise to keep the consistent light. After stacking comes enhancement, contrast stretch, deconvolution, sharpening kernels. Each step can help tease out real detail. Each step can also amplify the signature of the optics. Every scope has a fingerprint, slight asymmetries, tiny reflections, microscopic dust. If the target is smaller than a pixel or two, that fingerprint can masquerade as shape. Why did this image not get dismissed in a heartbeat? The observer is not a click farm. He has years of careful work on his channel. He documents equipment and settings. He speaks in measured language and even acknowledges uncertainty. That credibility matters. It slows the rush to label the frame as artful nonsense. It forces us to examine the method before we judge the conclusion. Look closely at the features that sparked the debate. The bright core looks elongated in a stable direction relative to the field. Secondary bright spots hint at prongs or protrusions. Ask two questions. Do those directions match any known optical artifact like astigmatism or a non-circular aperture? Do they rotate as the sky rotates or as the camera orientation changes? If the edges are locked to the instrument and not to the stars, that is a red flag for artifact. If the edges track with the sky, the case for structure gets stronger. There is also the question of color channels. Many enhancement workflows separate channels to boost contrast. That can create false edges at the boundaries where one band is noisier than another. Cross-checking the same feature in different filter bands is a sanity test. If a line exists in one band and vanishes in another, while the signal to noise is similar, the line is probably not real. Could an amateur reveal shapes that major missions missed? In rare cases, creative setups pick up phenomena because they stare longer and process with love. But there is a reason professional systems exist. They measure their optics to death. They calibrate on known fields every night. They publish error budgets so everyone can see how much to trust a line or a dot. The best amateurs adopt the same habits. When they do, their work stands tall beside institutional frames. Here is the part that makes this moment so combustible. Humans are pattern-making creatures. Give us a noisy field with a bright core, and we will see geometry. Faces in clouds, buildings in shadows. This is not a failure of intelligence. It is a side effect of a brain optimized to spot tigers in tall grass. Pareidolia is the name. Put aggressive sharpening on top of that, and you build a machine that forges meaning out of molehills. So what do we do with a viral image that might be artifact and might be revelation? We do not worship it. We do not burn it. We ask it to make predictions. If the edges are real, they should appear in independent captures from other observers using different optics. They should persist over time with changes that match the object's rotation and geometry. They should survive softer processing that errs on the side of caution. If the edges vanish when you tweak the sharpening radius, they were never edges. They were the ringing voice of the algorithm. There is a social dimension to this too. Platforms reward bold claims and crisp thumbnails. Slow nuance gets fewer taps. That does not mean we give up on the crowd. It means we channel the crowd, publish raw frames alongside processed ones, share exact settings, invite replication. The fastest way to kill a mirage is to shine a dozen different lights on it. The fastest way to grow a real discovery is the same. You may be wondering why the community reacted so strongly to one backyard frame. The answer is timing and vacuum. The institutional cameras were quiet. The object was about to slip behind the sundae. The world wanted a glimpse of the truth before the blind window. Into that hunger dropped an image that looked like an answer. The appetite did the rest. Hold that feeling and pin it with one rule. Curiosity without calibration is a rumor with better lighting. We are not here to crush wonder. We are here to protect it from turning into noise. The next wave made that harder. AI tools joined the party. Some outputs were obvious fakes with cinematic glow. Some were subtle and persuasive. A few were quietly unsettling. That is where we go next. We step into the enhancement wars and try to separate genuine signal from algorithmic hallucination before the feed buries both. When the backyard image went viral, the race to clarify or debunk it began. People pulled down every public frame of the visitor. They stacked, stretched, sharpened, and posted side-by-side collages. Standard stacking can help because noise behaves like chaos, while real signal repeats. Align many frames, average them, and the stable features emerge. That is the theory. The practice is messier. Alignment can drift, starfields can shift, the target can smear if tracking is imperfect. If the signal is marginal, stacking becomes an act of faith more than a measurement. Then, the algorithms arrived. AI upscalers promise miracles. Feed them a small image, and they generate detail that was not visible before. That promise hides a trap. These models are trained on large libraries of images. They learn the texture of metal, the crispness of edges, the common shapes of spacecraft and satellites. When the model meets a blurry point, it consults its history. The output can look plausible and exciting. It can also be a hallucination that fits the model more than the photons. The more striking the enhancement, the higher the risk that the algorithm has imposed its priors on the data. You saw the feed fill with impossible clarity. Some images suddenly showed panels. Others sprouted antenna-like shapes. A few gained dramatic lighting that felt like movie frames. Many were easy to dismiss because they changed with every tweak of a slider. A smaller group sat in a grey zone. They did not scream fake, they hinted. Lines looked too straight to be random. Brightness fell off with a neatness that teased geometry. Those were the ones that unsettled even careful viewers. Here is the heart of the problem. Once you push beyond the native information in the pixels, you are negotiating with mathematics rather than observing the sky. Deconvolution can sharpen the point spread function, but only within limits set by the signal-to-noise ratio. Past that threshold, the algorithm must invent. Sharpening raises local contrast. It also raises ringing around bright cores that can look like ribs or veins. Denoising can suppress speckle, but it can also smear away faint features that would have passed an independent check. Each knob is a choice. Each choice carries an aesthetic that can trick the eye. We need a compass. First, prefer methods that keep the data in its native sampling when possible. If you must upscale, document the factor and the model. Second, require that a proposed feature survive across independent stacks from different nights and different instruments. Third, test rotation. Real structure will rotate with the object, or with the sky. Instrument artifacts will rotate with the camera, or sit in fixed detector coordinates. Fourth, look for consistency across wavelengths. If a line only appears in one color band, even when the signal is strong in others, be cautious. We promise to anchor this investigation in checks that anyone can repeat. That promise matters most when the images look the most dramatic. Wonder is not fragile. It grows when we test it. There is also a social piece that deserves honesty. Attention is a currency online. Platforms amplify high contrast. Creators feel that incentive. Even careful people can drift into confident claims when a thumbnail and a title are competing with 1,000 other puzzles. That does not mean bad faith. It means we have to build norms that slow the urge to declare victory. When a frame looks shocking, the first job is not to celebrate it. The first job is to break it with replication. So where does that leave the viral edges that seem to hide in the glow? Right now they are interesting questions, not answers. Some could be echoes of the optics. Some could be the ringing of an aggressive kernel. A few might reflect real asymmetries in the coma, or jets of gas that create apparent edges. There is a clean way to find out. Correlate features with time and with rotation. and compare across independent sites. If they live, they will show their own rhythm. You might ask why we are spending so much time on workflow when the sky is full of bigger mysteries. Because workflow is how you keep from fooling yourself. In a story that already carries public frustration and institutional silence, the danger is not that we will miss a signal. The danger is that we will build one out of enthusiasm and see exactly what we trained our tools to show us. All of this set the table for the next turn. As the enhancement wars raged, a post appeared that did not show images at all. It listed numbers, spectral lines that did not match expectations, thermal behavior that defied simple heating, a trajectory that seemed too precise to be random. It claimed access to agency data and invited anyone to check the physics. It read like a dare. If those claims were true, the debate would change. If they were not, they would collapse under scrutiny. That is where we go now. We test the list, one line at a time. An anonymous post landed with the confidence of a lab memo. No dramatic images, just claims and numbers. 3 anomalies, each strong enough to bend the entire debate if confirmed. Nickel emission without corresponding iron. Intense outgassing while the object stays cold in infrared. An arrival that looks too precise to be random. Could all 3 be true at once? Or are we looking at a stack of misunderstandings that feel profound only because they are stacked? Start with the chemistry. In the cosmos, nickel and iron are close companions. They are forged together in stellar furnaces, scattered together by supernovae, and found together in meteorites and cometary dust. Spectra of comets often show neutral and ionized lines from both families. The leak claims a strong nickel signal with iron barely present. That reads like smoke with no fire. If accurate, it points to an enrichment process that sorted elements with nearly identical histories and similar atomic weights. Nature can fractionate materials through repeated heating and venting, and through photochemical effects, but nickel without iron at the levels suggested would be extreme. If this is real, it should survive independent analysis with public spectra. Cross-check against archives, look for the same lines in different instruments. Confirm that the wavelengths match nickel rather than a blended neighbor. If the lines move with the object, not with the background, the case strengthens. If they wobble with the calibration lamps or stay fixed while the target shifts, the story collapses. Now, the thermal claim. The post argues that the object vents large amounts of gas and dust, yet infrared observations find the core colder than models predict. Normally, sunlight heats the surface. Sublimation soaks up energy and produces a coma. If you see heavy outgassing, you expect a surface that is at least warm within model bounds. A cold result alongside strong venting means the energy is going somewhere else, or the emission is dominated by small grains that radiate inefficiently. There are subtler wrinkles. Porous materials can move heat inward. Rotational states can expose and hide fresh ice in patterns that confuse a single snapshot. If the object has an isothermal layer or unusual thermal conductivity, the naive expectation breaks. Here is how to test the claim. Demand a multiband infrared curve that ties brightness to blackbody fits across time. Compare with gas production rates inferred from known lines like carbon monoxide or water. If the thermal power and the mass loss refuse to balance after you include rotation and grain size, the anomaly survives. If a notch in emissivity or a revised size estimate restores the books, it fades. The trajectory is the cleanest of the 3 to audit. The post describes an arrival within a few degrees of the ecliptic and hints at a straight shot from near the galactic center direction. Interstellar visitors should come in from many angles. We have seen that with previous examples that arrived at steep inclinations. This one sits under 5 degrees relative to the plane of the planets. That is rare, under simple assumptions. Rare does not mean guided. To evaluate this, you do not need secrets. Orbital elements are public math. You can compute the inclination and the inbound radiant. You can estimate how likely that geometry is under different priors. You can also check whether small perturbations by planets on the way in could have nudged the object toward a shallow angle. If the statistics hold after that work, the trajectory remains a head-scratcher. If selection effects and gravitational focusing account for much of the surprise, the puzzle shrinks. At this point, you might feel the pull of the dramatic frame. If nickel appears alone, if heat disappears while gas pours out, if the path looks deliberate, then we are staring at something built rather than born. That is a powerful narrative. It can also be a trap. We promise to keep facts and inference in separate hands. So we ask the leak to do the only thing that matters, produce methods and let others test them. What instrument measured the lines? What calibrations were applied? What models were used for thermal fits? What ephemerides generated the trajectory plots? Without that scaffolding, we only have a story. Curiosity is our engine. Reproducibility is our brake. We will not ride without both. There is one practical reason to take the leak seriously enough to check, and not a step more. Each anomaly invites a concrete observation. Nickel without iron invites spectra from independent telescopes along the same sightline. Cold with venting invites simultaneous infrared and gas line monitoring to close the energy budget. A too precise path invites an open calculation that anyone can repeat. We are not waiting on a single gatekeeper to unlock these doors. The community can push on all three. There is also the social weather to consider. Anonymous voices land harder when official channels are quiet. In a normal week, a post like this would be a curiosity. In a week of blur and silence, it feels like a key. That is why clarity matters. If any part of the leak survives independent checks, we will say so. If it fails basic replication, we will say that too. Either way, the result strengthens trust. Speculation did not stop at these three claims. It grew into bolder ideas that try to make all the puzzles rhyme at once. Some people reached for a post-biological concept. Others reached for exotic states of matter that could move energy around without obvious heating. Those are large claims. Before we touch them, we will lay out what those ideas actually propose and the narrow way they might explain the chemistry and thermal behavior without magic words. Then we will bring the same discipline to them that we, brought here, ask for predictions, ask for tests, ask for the next measurement that would force us to update our beliefs in either direction. What is a cue ball? In field theory, it is a stable lump of a scalar field that behaves like a single object. It can spread energy through its body in a way that does not look like ordinary matter. In some models, a cue ball can be large. It can be diffuse and oddly cool while still moving energy around inside. That picture is strange, yet it has a motive. It tries to explain cold infrared readings against signs of strong outgassing. It tries to explain chemistry that sorts elements which usually travel as twins. It is a thought tool, not a conclusion. Post-biological is another idea that jumped from forums into the mainstream. The phrase points to a technology that does not look like ships and thrusters. Imagine a self-regulating structure that behaves more like a mineral or a gel than a metal craft. It could harvest or redistribute energy without leaving obvious thermal scars. It could vent material in patterns that look natural while steering with internal physics that we do not use. That is a story. It earns time only if simpler stories fail across many independent checks at once. There is an old rule that saves many investigations. Reach for exotic physics only after you have exhausted ordinary physics with discipline. Ordinary physics is still very rich. Porous, icy bodies can move heat inward in counterintuitive ways. Grain size and composition can shift emissivity and break the neat link between gas production and measured temperature. Jets can create brightness asymmetries that mimic edges. Rotation can turn on and off vents in a way that confuses single snapshots. Before cue balls or post-biological machines, we must press these knobs as far as the data allows. Yet the speculative ideas help if they make predictions that simple models will not. A cue ball-like object should couple poorly to sunlight across familiar bands. Its thermal curve would stay flat while activity changes. It might respond to magnetic fields in ways a comet does not. A post-biological object should be able to change its path with a thrust profile that does not match gas jets. It could hold attitude against solar radiation pressure with a stability that looks like control. Both classes might produce narrowband radio features that drift exactly with relative motion rather than with outgassing cycles. Those predictions set clean tests. Watch the thermal brightness across several infrared bands at the same time as gas lines like water and carbon monoxide. If activity rises while the thermal curve stays flat beyond what porous models can support, the simple story bends. Measure tiny course changes and compare them to times when spectrometers see strong venting. If motion changes without venting, or if the changes look like impulse rather than a slow push, the simple story bends again. Aim radio dishes at the hydrogen line and nearby, and look for tones that repeat and drift with Doppler in a way that nature does not usually produce. There are also geometric tests that sit inside the blur. A technological structure would show persistent geometry in the coma after you account for the point spread function. Subtle? Yes. Impossible? No. If independent teams with different optics report the same skew in the light profile at the same position angle, and the skew rotates with the object rather than with the camera, that is evidence. If polarization maps show stable vectors that suggest aligned surfaces rather than random dust, that is evidence. We should also be honest about failure modes. Exotic narratives thrive in missing context. Give them the rover streak without exposure metadata and they will build a tower. Add a 10-minute integration time and it becomes a smear. The cure is not mockery. The cure is data that closes doors. That is why we keep asking for methods, for calibration files, for timing stamps, for star matches that lock down pointing. When those arrive, many wild branches will prune themselves. Curiosity invites wild ideas. Discipline tames them. We can carry both without apology. We keep a space on the table for strange physics, but we bill it for rent with predictions and with deadlines. All of this sets up the next turn. A single rover frame seemed to show an object as long as 50,000 kilometers. That number landed like thunder. Then the math arrived with a calmer voice and a single missing detail that still bothers people. If you want to see how a mystery can shrink to a calculation and still leave a splinter, come with me to the Martian night and the long bright streak that everyone argued about. A single frame from the Martian night set off a wave of claims. The Perseverance right navigation camera recorded an elongated streak that looked impossibly long at the visitor's distance. Screenshots spread. Captions shouted, "Was this a megastructure the length of a planet? Or was it a trick of time and motion?" The answer lives in a few lines of geometry and one piece of missing metadata. Start with how a camera sees the sky. A sensor does not record length, it records angle. The navcam has an angular scale of about 0.33 milliradians per pixel. If the object sits around 38 million kilometers away, each pixel spans roughly 12,500 kilometers at that distance. Count the streak across the sensor. You get near 4 pixels. 4 times 12,500 gives you about 50,000 kilometers. That number is shocking. It also begs a question. Did the camera record a shape, or did it record a path traced during the time the shutter was open? Now, bring in motion. Mars orbits the Sun at about 24 kilometers per second. The interstellar visitor was moving near 60 to 70 kilometers per second relative to the Sun in the opposite direction. That sets a relative speed near 90 kilometers per second against the Martian sky. Multiply that by integration time. Over 10 minutes of exposure, the object would traverse around 54,000 kilometers in projected distance. That lines up beautifully with the length of the streak. If the frame is a composite, or a stacked integration across many seconds or minutes, the bright path is the object, drawing a line through space while the camera watched. The apparent size is not the size of the body. It is the distance traveled while the sensor collected light. There is a quiet elegance to that calculation. It turns a viral shock into a familiar lesson. Long exposure photography makes trails. We have all seen star trails from a fixed camera on Earth. This is the same idea turned inside out. Track stars or track the ground, anything that moves relative to that reference will smear. Fast objects smear more, bright objects smear brighter. Then comes the splinter. If the navcam frames were single snapshots with short exposures, the smear explanation breaks. There would not be enough time to draw such a long line at that angular speed. A short exposure would force another conclusion. The bright streak would have to be a nearby source crossing the field. Something closer to the camera, a satellite glint, a cosmic ray-like track, a faint meteor in the thin Martian air, a reflection from within the optics. The only way to close that branch is to know the integration time and the stacking procedure for that exact frame. This is why missing metadata hurts more than any blur. One number could settle the argument. Was it one long integration? Was it a stack of shorter exposures aligned on the stars? Was there onboard processing that combined frames for navigation purposes? Each option leaves a distinct signature. Each option would turn the streak into either a lesson in motion or a hunt for a different local cause. There is another detail that can help when the metadata is slow to arrive. Look at the edges of the streak. Long integration trails often show a uniform intensity profile that fades near the ends as the object enters and leaves the field of view. If the streak has sudden brightening or dimming that repeats at regular intervals, that can indicate tumbling or rotation of a nearby object. If the width of the streak is constant and matches the point spread of stars in the same frame, that supports the long exposure motion case. If the width is different, that points to a different kind of source. We should also talk about the human part of this controversy. Numbers calm the mind, but the image itself is provocative. 50,000 kilometers feels like ore turned into evidence. The temptation to see a body that large is strong. That is why we write the math out loud. That is why we ask for the missing line in the header file. Because once the exposure time is clear, the interpretation is clear. Either the streak is a sidewalk chalk line drawn by a fast traveller during a long watch, or it is something else closer and local that happened to cut the frame at just the right moment. We accept uncertainty where the data is incomplete, and we show exactly what would resolve it. That keeps excitement honest without draining it. With the streak placed back into physics, another thread pulls at the edge of this story. Decades before this visitor arrived, a radio telescope in Ohio heard a narrowband signal from near the hydrogen line. It came from a patch of sky not far from the direction this object took as it entered the inner system. The odds of such an alignment are not large. They are not zero either. So is that geometry a coincidence, or is there a deeper link waiting to be tested? The next part takes us back to the summer of 1977, and the moment an astronomer circled a set of numbers and wrote a single word in red ink. In the summer of 1977, an Ohio radio telescope caught a whisper that still lives in the margins of a printout. 72 seconds of narrowband power near the hydrogen line. An astronomer circled the numbers in red and wrote one word. Wow. It never repeated. It never explained itself. It simply sat there like a dare to the future. Now, fast forward to our interstellar visitor. Reconstruct the path it took as it fell into the inner system. Project that path backward across the sky. The inbound radiant sits within single-digit degrees of the region where the wow signal appeared. That alignment is not proof of anything. It is also not nothing. In a sky of 40,000 square degrees, single-digit separations are rare under simple chance. Low probability is not intent. Low probability is a reason to check. Let us turn the mystery into numbers we can test. The wow burst sat just off the hydrogen line near 1,420 MHz. That is a natural watering hole for radio astronomers because neutral hydrogen glows there, and advanced senders might choose that channel as a universal signpost. The signal was narrow. It rose and fell across about a minute as the beam of the telescope scanned past. It did not carry modulation we could decode. It did not return on later nights. Could our present visitor have sent that burst from deep space almost 5 decades ago? If the object sat a few hundred astronomical units from Earth in 1977, how powerful would a transmitter need to be for Big Ear to hear it? The estimate lands around fractions of a gigawatt to a couple of gigawatts into a tight beam. That is a serious energy budget. It is not absurd for a technological source. It is out of reach for a natural process that produces broadband noise rather than a single clean tone. Here is the part that should be easy. Aim modern dishes at the visitor today and listen, not once. Night after night, use coherent receivers that can watch a slice of spectrum centered on the hydrogen line and nearby. Correct for Doppler drift in real time as the object moves. Look for a tone that persists across minutes and hours and slides exactly as the relative velocity predicts. If the tone appears, we will know almost at once. If it does not, the wow connection moves back into the cabinet of coincidences. So why have we not seen a steady stream of listening reports already? Part of the answer is mundane scheduling. Big facilities juggle many programs, and sensor time is precious. A short-term target of opportunity competes with long-planned projects. Another part is institutional caution. Announcing a null result eats time and reputation when a target is controversial. There were also weeks when government shutdowns complicated ordinary operations in the largest programs. Even so, the absence of public reports feels like a gap we ought to close. This is not only a job for national arrays. University dishes can stare at the right patch with modest systems. A handful of amateur radio astronomy groups can also try, as long as they calibrate against known beacons and share raw streams for cross-checks. The protocol is simple. Record spectra with high resolution. Tag every file with precise time. Publish the Doppler model you used. Let others reprocess the same data with different assumptions. If a tone lives there, redundancy will find it. If noise mimics a tone in one setup, the mirage will vanish under replication. We should also level with ourselves about what a positive would and would not prove. A single detection near the hydrogen line that drifts as predicted would be astonishing. It would not tell us intent or content. It would say that something at that location is radiating in a way that natural comets do not. Repetition would matter. Modulation would matter. Polarization would matter. A negative would not kill the story. It would simply move weight from one branch of explanation to another. That is how honest inference works. Let us pause for a breath and reorient the thread that carries us. Through this series, we keep converting online emotion into checkable steps. When we do that, the narrative slows down in a good way. It becomes a staircase rather than a jump. There is one more angle to this alignment that deserves a clear head. Geometry is seductive because the human brain loves lines that meet. The galaxy also gives us many chances to draw lines if we look long enough. The wow patch covers a region rich with stars. The visitor could pass within a few degrees of many famous directions purely by chance. That is why we do not crown a champion based on a map overlay alone. We use the overlay to motivate hard observations that either find a present-day signal or do not. The wow thread hands us to another statistical itch that will not go away. Even if you forget the radio story, the arrival angle of this object is still unusual. Interstellar visitors should fall in from many angles. Our earlier examples did. This one skims almost in the plane of the planets. That is a narrow slice of the possible sky. A single oddity is just a quirk. A pattern of oddities is either selection bias or a new story waiting to be told by better models. The next part takes that angle seriously and asks how unlikely it really is under different assumptions and what that means for how we frame the whole debate. If you tossed darts at a globe while blindfolded, you would not expect them to land near the equator every time. Interstellar objects are those darts on a cosmic scale. They can arrive from almost any direction. Our first two examples did exactly that. The first took a steep path with an inclination over 100 degrees relative to the plane where planets orbit. The second arrived around 40 degrees. Our current visitor skims in at under 5 degrees. That is a very thin slice of sky. Why does that matter? The ecliptic is the reference plane set by Earth's orbit. Most planets ride near it. Debris and dust in our neighborhood tend to align with it. Interstellar travelers are not born here. Under simple assumptions, their approach directions should scatter broadly across the celestial sphere. Shallow arrivals should be rare if you pick a random trajectory from faraway space. That is the intuition behind the claim that this path is suspicious. Now we test the intuition. First, ask what our telescopes are more likely to notice. Surveys often scan near the ecliptic because that is where many solar system bodies live. That choice can bias discovery towards shallow approaches. If you look where the fish are, you catch more fish. The question is how strong that bias is for fast hyperbolic objects. Next, ask how gravity nudges trajectories. As an object falls toward the sun, encounters with giant planets can bend its path. Gravitational focusing by the sun itself can also skew the set of apparent approach vectors for what we actually detect. These effects could fatten the fraction of low inclination arrivals compared to a naive random model. There is a second frame worth considering. The galactic disk is tilted by about 60 degrees relative to our ecliptic. Many stars that could launch visitors live in that disk. If you eject objects randomly from systems in that disk, the average arrival directions in our sky do not line up with the ecliptic. They spread across a band that usually meets our plane at steep angles. That makes a shallow arrival look even more unusual under that prior. A full answer requires models that mix the true survey strategies with the true spatial distribution and velocities of sources. Simple back-of-the-envelope arguments can suggest that a few % of arrivals might be shallow. They rarely put that number under 1% unless you lock in strong assumptions. Here is where discipline matters. Low probability is not the same as design. Courts warn about the prosecutor's fallacy for a reason. If you list only the events that surprise you after the fact, you can make any ordinary world look haunted by intention. The fix is to define tests in advance, or to use models that include the way you looked and the way you chose your sample. That is why some teams will disagree on the exact odds for this path. They choose different priors, they include different selection effects, they get different answers by a factor of a few. All of them agree on one point. This approach is not typical. It sits on the thin end of the distribution. So what do we do with a trajectory that looks uncommon? Alone, it is a curiosity. Combined with other tensions, it becomes a tile in a mosaic. The right move is not to crown a theory. The right move is to keep collecting tiles and to keep asking whether they are truly independent. A rare arrival angle plus a cold infrared curve plus odd chemistry would mean more together than any one piece alone. A rare arrival angle plus a long exposure smear plus ordinary chemistry would not. We keep turning drama into measurements and feelings into models. This keeps our footing while the story pulls us forward. Curiosity stays high, claims stay humble. There is a human layer that now enters the frame. When the path looks strange and the best cameras take their time, the conversation slides from science into culture. Posts vanish without warnings. Creators report sudden drops in reach. Fact-check panels attached to routine math. People start using coded words to dodge filters. Whether you call that moderation drift or algorithmic weather, it shapes what the public hears. In the next part, we look straight at that social turbulence, not to feed conspiracies, but to understand how opaque systems can amplify suspicion exactly when patience is most needed. The week the blur dropped, the conversation began to feel sticky. Posts about the object appeared, climbed for an hour, then vanished or stalled. Creators who normally reached a city worth of viewers watched numbers freeze at a small town. Some videos that argued for simple, natural explanations were fine. Others that walked through anomalies tripped yellow icons and lost ads. A few channels saw fact-check panels attached to basic math. None of that proves a plan. It does shape a mood. Algorithms are not referees with whistles. They are vast stacks of pattern finders tuned by incentives and safety rules. When a topic catches fire and carries even a whiff of risk, the system leans toward caution. Words that once flowed begin to drag. That feels like being hushed even when no one says be quiet. You can feel the psychology kick in. If you think you are being throttled, you become louder or you go coded. Either way, the original signal gets distorted. This is where trust takes the hit. Science needs open corridors. Viewers need to know what is conjecture and what is data. Creators need to know what boundary they are about to cross. Opaque decisions turn those needs into guesswork. Guesswork grows suspicion. Suspicion then spreads faster than context. People invent nicknames for the object so that filters do not trip. They swap words like alien for softer phrases that mean the same thing. The language bends around the rules and becomes a secret handshake. That might help a channel survive. It does not help the public think clearly. We can do better without blaming ghosts. Platforms could show clearer labels when a post is limited. They could separate three things that often get blurred: safety policy, quality of evidence, suitability for advertisers. Those are different questions. When they are mashed together, a notice that should read this topic needs careful context turns into this creator is pushing junk. Scientists and educators could also help. Pre-publish short explainers that list what a new frame can and cannot show. Share templates for how to disclose uncertainty in plain language. Make the honest path easier to follow. There is also a way for viewers to reclaim agency. Ask for raw data links whenever someone shows a stunning enhancement. Reward creators who publish settings and calibration details. Share work that separates facts from inferences. You can nudge the attention economy toward rigor with your clicks. Curiosity and care are not enemies. They are partners. If you want more of both, feed more of both. We are turning heat into light by asking for checks that anyone can repeat. That promise still holds even in the messy lanes where culture and code meet. The goal is not to win an argument with a platform. The goal is to keep the investigation clean enough that it survives the feed. Some of you wrote that you felt whiplash. One day there is a blur and 1,000 takes. The next day your favorite channels go quiet or start speaking in riddles. That dissonance makes the silence from space agencies feel louder. It stacks with the sense that time is running out to see anything meaningful. Those feelings are real. They are also the exact moments when a story needs a clock and a plan. The clock is not ours. It belongs to the orbit. The object is heading for its closest approach to the Sunday. From Earth, it will be hidden in glare during the days when heating could make it most dramatic. Ground-based telescopes will be blind. Social feeds will still spin, but the sky will not answer for a while. That window is coming fast. It will test our patience and our process. Here is the plan. We will keep our eyes on what can be measured before and after the blind period. We will ask for the metadata that closes open cases. We will look for coordinated observing runs that can catch the reappearance with enough coverage to check for course changes and fresh activity. Most of all, we will stay honest about what a pause in visibility means. A pause is not proof of anything. It is a reminder that nature sets the schedule. If this investigation has kept you curious and calm, share it with someone who loves space and good puzzles. The next chapter is the hardest kind of waiting. The sky fades to glare. Instruments on the ground go quiet. Hopes go loud. And yet this is the part of the story that teaches the most. What do we do when we cannot watch? We prepare for the moment the light returns. The most important act in this story will play out while the lights in our theatre are off. The object will swing closest to the sun during days when the sun blinds every ground-based telescope on Earth. The scene will unfold in the glare. Our instruments will blink. The audience will murmur. The sky will say nothing. That silence is not a signal. It is geometry. When an object passes behind the sun from our point of view, scattered light floods our optics and smothers faint targets. That happens every year to planets and comets. It feels personal this time because curiosity is running hot and time feels short. The rule still holds. The sun wins every staring contest. So what should we expect during the blind window? If this visitor is a normal comet, heat should rise as solar radiation climbs. Sublimation should accelerate. Gas jets should strengthen. The coma should expand. Dust production should spike. In the most dramatic case, internal stresses could fracture the nucleus. We might see the body split into several pieces, each with its own cloud. Many comets have done exactly that during close approaches. If this is ordinary ice and rock, solar energy has 100 honest ways to leave its mark. What if it is not ordinary? The test is simple to state, hard to watch in real time. A technological object could use perihelion as a chance to change course with precision that gas jets do not deliver. It could tighten or loosen its path with brief impulses that do not match measured bursts of venting. It could release small probes that fall inward on intercept trajectories. None of those ideas are foregone conclusions. They are scenarios that many viewers have asked us to address. The key is to translate every scenario into signatures we can check once the glare lifts. Before we list those signatures, it is worth addressing the human stakes. Markets dislike uncertainty. Newsrooms like vivid phrases. A few lines have already suggested that abrupt maneuvers toward Earth would rattle finance and policy. That kind of statement is true in the abstract and unhelpful without context. Risk communication works best when you keep the focus on measurements and thresholds. We will do that here. We will say what numbers would count as extraordinary and what numbers would be normal. That keeps fear honest and curiosity alive. Here is a calm plan for the blind period. We do not chase every rumor. We prepare for first light on the far side. Observatories map out their windows for early November. Teams set up pipelines to compare predicted positions with actual positions. Radio facilities schedule listening blocks centered on the hydrogen line and adjacent bands. Amateur networks coordinate targets so that gaps in professional coverage are as small as possible. When the object reappears, we will get a short but rich window. Preparation turns that window into answers. We began with a blur that fed frustration. We followed the math that explains the blur. We watched as a silence from major cameras collided with a surge of amateur processing and speculation. Now the orbit gives us a forced pause. Our method does not change. We turn attention into checklists. We turn checklists into observations the moment the sky allows it. There are small things we can still learn during the glare. Spacecraft that are not blind to the sun can attempt observations if geometry and safety allow. Some coronagraphs can suppress solar light and pick out bright comae near the limb. Those options are limited, yet they are not zero. If any team collects data in that window, the key will be rapid and careful calibration. A single well-documented frame can do more than a dozen hurried ones. Patience does not mean passivity. You can help keep the investigation clean. Resist claims that rely on unseen insiders. Ask for timestamps, filters, and exposure times. Ask if the imaging was tracked on stars or on the target. Reward creators who mark what is known and what is guessed. A healthy audience can raise the standard of the whole conversation. When the light returns, early measurements will matter. The first numbers to watch are position and velocity. If the post-perihelion trajectory matches predictions within normal uncertainties, the case for a natural comet strengthens immediately. If not, the size and timing of the deviation will tell us a lot. Next comes spectra and photometry. If outgassing has surged, lines from water or carbon monoxide should rise in strength in ways that match heating models. If activity remains muted despite peak solar input, that is interesting and testable. The final point in this chapter is humility. Nature loves to surprise us, but it rarely rewards impatience. The blind window is frustrating because it falls at the most dramatic moment. It is also a gift because it forces us to define in advance what counts. When we say out loud what would change our minds, we protect ourselves from moving goalposts once the data arrives. We are about to step from darkness back into light. The next part lays out the signatures that truly separate ordinary from extraordinary, clear, concrete, and public. When the first post-perihelion frames and spectra land, those signatures will let you judge the claims for yourself without relying on anyone's headline. If we want a clean line between ordinary and extraordinary, we need signatures that do not care about headlines. These signatures should be visible to different teams using different tools. They should point in the same direction even when processed with different methods. When that happens, doubt shrinks and confidence grows. The first signature is geometry in motion. Astrometry will tell us if the post-perihelion path hugs the predicted curve or slides away from it. Small drifts that match the direction and timing of measured gas jets are normal. Drifts that begin without corresponding activity or that reverse in ways gas cannot produce are not normal. A precise impulse that changes velocity at a specific moment without spectroscopic evidence of a burst is a red flag for control rather than venting. The second signature is chemistry with timing. If sunlight drives activity, then spectra for water, carbon monoxide, and simple radicals should rise and fall with a pattern tied to solar input and rotation. A surge in brightness should carry lines that grow in step with photometry. If brightness steps up while lines stay flat, that suggests processing artifacts or dust-driven effects that need explanation. If motion changes while gas lines do not, then something other than vents is at work. The third signature is structure in light. Even below image resolution, the shape of the coma can carry clues. A normal coma has a smooth radial profile that falls with distance in a predictable way. If independent teams recover a persistent skew or an edge that rotates with the object rather than with the camera, that is interesting. Polarization maps can turn interesting into compelling. Random dust gives messy vectors. Aligned surfaces give stable vectors that track a fixed attitude. If polarization stays steady through rotation cycles, that hints at structure that holds its orientation. The fourth signature is thermal balance. Infrared bands tell us temperature and effective size. Gas lines tell us mass loss. The energy that goes into vapor must come from somewhere. If the object vents heavily while the thermal curve stays colder than models allow, we tighten every ordinary knob first. Grain size, porosity, rotation state, and emissivity can fix many surprises. If the mismatch survives that audit across multiple nights and multiple instruments, the simple picture bends. The fifth signature is radio behavior. Nature does make narrow lines, but they do not sit like clean tones near the hydrogen line and then drift exactly with relative motion for minutes at a time. A repeatable tone that slides with the Doppler model and appears in independent receivers is hard to wave away. Modulation would be even harder to ignore. A null result is also a result. If careful searchers hear nothing, the weight of the story shifts back toward ice and rock. The sixth signature is fragmentation physics. If the nucleus splits, the pieces tell a story. Natural breakup produces fragments that fly apart with speeds and directions that agree with stress models and vent geometry. Artificial release would look different. Fragments would appear with matched velocities, or with deployment timing that does not track thermal strain. Light curves for individual pieces would reveal whether they behave like fresh ice or like inert shells. There is one more practical proof that sits between images and equations: replication with transparency. If a feature survives when different teams use different telescopes, different filters, and different processing chains, it is real. If a claim only lives in one stack with one aggressive algorithm and dies when the settings change, it was never alive. That is not gatekeeping. That is how we keep from fooling ourselves. When the sky opens after glare, these are the yardsticks to hold. Position and velocity first, then spectra and photometry, then shape and polarization, then infrared balance, then radio. Then the physics of any fragments. No single measure needs to carry the case. Together, they will paint the answer in colors that hold under scrutiny. In the next chapter, we look at who will be watching and how the community can turn many small eyes into a single clear view. Coverage matters because strange events do not schedule press conferences. Preparation turns chance into knowledge. Patience turns knowledge into wisdom. We are almost at the part where those virtues pay off. When the glare fades, there will be eyes waiting. Some are university observatories with modest mirrors and excellent timing. Some are hobbyist rigs with surprising reach run by people who log every exposure like pilots. A few are dedicated stations built precisely for anomalies. They do not look like movie sets. They look like workbenches that never sleep. Small teams have an edge in moments like this. They can schedule quickly. They can point and shoot without 3 layers of approvals. What they lack in aperture, they make up in cadence. A fast sequence of honest frames can beat a single masterpiece if the goal is to catch motion and change. If you can measure the center of light precisely across many frames, you can extract a path that rivals bigger facilities, which only visit once. Coordination multiplies power. If stations agree on filter sets and cadence, their data stacks into a single time series that covers more hours. If they stagger geographic longitudes, the night follows the object around the world. If they use the same reference stars and publish their astrometric catalogues, anyone can combine their measurements without guessing. Many small eyes can act like one larger instrument when they share habits. False positives will bloom. High curiosity phases always do that. Satellites will drop flares across frames. Airplanes will paint neat lines. Thermal noise will imitate faint points at the threshold of vision. Protocols help. Log times in coordinated universal time with sub-second stamps. Record exact exposure lengths and whether you track the stars or the target. Include the raw files along with processed products. These details sound boring. They turn noise into solvable puzzles. Some groups will aim radio antennas rather than cameras. Even modest dishes can watch the hydrogen line with fine resolution. The trick is stability and calibration. Point at known beacons to make sure your frequency scale is honest. Remove local interference by mapping your own environment. Share raw spectra along with your waterfall plot so others can apply different Doppler models. If a tone exists, you want redundancy to find it. If a glitch lives in one receiver, you want others to prove it was local. There is humility in this kind of watching. No single station can see everything. The sky is large and equipment breaks. Clouds roll in, power flickers. That is okay. The goal is not perfection. The goal is enough overlap that gaps do not matter. If a fragment splits from the main body and only one camera sees it, replication will be slow. If 3 sites see it within an hour, the confirmation is routine. Let us pause and reorient the thread that guides us. We keep pairing urgency with structure. Eyes on the sky are not enough. Logs, methods, and sharing rules turn images into knowledge. Without them, images are just pictures that argue well on social feeds and settle nothing. The largest agencies will re-enter the conversation too. When their pipelines catch up, they will publish carefully calibrated products with error bars and caveats. Those will be the anchors that smaller teams tie into. Do not be surprised if the institutional frames look plainer than the internet hoped. Plain can be powerful. A stable brightness curve with honest uncertainties can crush 3 weeks of rumor. There is also a bridge between worlds that matters here. Citizen observers who adopt professional discipline become part of the core evidence. Professionals who speak accessibly about limitations keep the public engaged without feeding fantasies. That bridge is not a slogan, it is a practice. Share raw, share methods, share doubts. Invite checks. We should admit something else. This watch is also about morale. After a stretch of silence and speculation, nothing steadies a community like the return of clean data. A single night of crisp astrometry and spectra will feel like rain after drought. That feeling is not trivial. It fuels the patience to keep going when the next surprise arrives. The next step in our story sits behind the scenes, where bits turn into plots. Data moves from instruments through calibration chains before it ever touches a public page. That journey is slow for reasons that protect truth. It can also be painfully slow when curiosity burns hot. In the next part, we will walk that pipeline. We will see where the data sleeps, why it naps so long, and what could shorten the nap without breaking the science. Before photons become pictures on your screen, they pass through a long, careful gauntlet. Spacecraft do not send images as simple files, they send packets. Packets get stitched into frames. Frames carry housekeeping numbers about temperature, voltage, and pointing. Only after engineers are sure the bit survived, the trip do scientists begin the part the public imagines when they hear the word image. The first stop is instrument calibration. Teams subtract bias and dark current. They correct for bad pixels. They apply flat fields that remove uneven sensitivity across the detector. They measure the point spread function so that a dot of light behaves the same way across the field. None of this is optional. Skip a step, and you can create shapes that are not real or erase structures that are. Next comes geometry and time. Star fields in the image are matched to catalogs to lock down pointing. The clock on board is reconciled with ground time so every exposure has an honest timestamp. The spacecraft attitude during the exposure is folded in. If the instrument scanned, or if the target moved relative to the stars, that motion is modelled. Without this stage, you cannot measure where an object truly is or how fast it crosses the sky. Then the radiometry team turns counts into light. Detectors record electrons. Scientists need brightness in physical units. They check calibration lamps, reference stars, and past observations to convert numbers into flux. They estimate uncertainties. They flag frames that carry unusual stray light or saturation. They annotate everything so that a reader 6 months later knows which values are rock solid and which are soft. Only now do the products begin to look like the images you expect. Even at this point, there are versions. There are quick-look products that are good enough to tell the team whether they caught the target. There are level 1 products that include basic corrections. There are higher-level products that fold in detailed models and deeper checks. The higher you climb, the slower the release, because every added correction needs verification and sign-off. Why does this matter for our story? Because a single line of metadata from this pipeline could settle arguments. If the rover streak exposure time and stacking settings were published, the smear math would either stand or fall. If the navigation solution for a Mars orbiter frame were shared, astrometry could tighten without delay. When silence follows a viral claim, remember that most of the work is hidden in these plumbing steps, where no one gets applause and every mistake haunts future conclusions. There is also policy layered on top of the pipeline. Many missions grant their teams a proprietary period. It is a short window during which the people who built the instrument get first crack at their own data. That period protects careers and ensures that rushed outside analyses do not mislead the public. The price is patience. During shutdowns or budget freezes, even routine public portals can go quiet while the pipeline continues in the background. That makes a normal delay feel theatrical when an audience is keyed up. Sometimes the delay is structural. A European mission around Jupiter plans to observe the object in early November. The downlink will trickle through limited bandwidth. Teams will process and validate. Public release is scheduled for a later month so that calibrations are correct, and documentation is complete. The dates feel slow because curiosity runs hot. They are chosen to keep the science honest. Could any of this move faster without breaking trust? Yes, with guardrails. Agencies can publish quick-look images and essential metadata with bold labels that say preliminary. Teams can mirror raw packets and basic headers to public archives while higher-level products cook. Observers can release exposure times, filters, and tracking choices, along with small cutouts, so that independent checks are possible without compromising full analyses. Citizen pipelines can replicate basic calibrations if the reference files are shared. Speed and rigor can coexist if everyone marks what is raw and what is refined. Let us reorient our thread for a moment. Our goal is not to scold caution or to celebrate speed for its own sake. Our goal is to make the path from photons to proof visible. When that path is clear, patience stops feeling like secrecy and starts feeling like craft. That shift in feeling matters. It steadies a community that has been running hot. The pipeline is the backstage. The stage lights will come up again soon. When the object emerges from glare, planning will matter more than emotion. Early frames and spectra will arrive. The best use of them will depend on whether we are ready to compare prediction to reality in the first hours. In the next part, we step from the lab bench to the sky and lay out exactly how to watch the return in a way that turns minutes into answers and answers into calm. The glare will fade. The sky will give us minutes that matter. When those minutes arrive, we do not guess, we measure. Here is the clean order of operations that turns first light into answers you can trust. First, we pin down where it is. Astrometry comes first because position and time are the backbone of every later claim. Point, expose, centroid the core, and solve the field against a star catalogue. Submit the measurement with precise time and your reference. Stars. Repeat quickly to build a short arc. Compare that arc to the predicted track. If the points ride the curve within known uncertainties, you are looking at normal behaviour. If they drift in a way that exceeds the budget, mark the size and direction of the delta. The geometry will tell us if any force beyond outgassing is at work. Next, we take the temperature of the coma. Photometry and a few filters gives a quick brightness curve. Spectra add chemistry. If heating drove activity during the blind passage, lines for water or carbon monoxide should rise in step with total brightness. If the flux jumps with no matching lines, that hints at dust physics or processing artifacts. If the flux stays flat when heating should peak, that is interesting. Keep the tone calm and keep the files open. Structure comes after brightness. Even below image resolution, the light profile holds clues. Fit the radial fall-off and look for a persistent skew. Map polarization if you can. Random dust produces messy vectors. Aligned surfaces produce stable vectors that hold an attitude. If the skew rotates with the object and not with your camera, and if polarization stays steady through rotation, that is a clue that geometry is hiding in the glow. Infrared tells us if the energy budget closes. Short and mid-infrared bands give an effective temperature and a size estimate. Gas lines tell us mass loss. The power needed to vaporize that mass should show up in the thermal curve. If venting is strong and the curve is cold, push every ordinary knob first. Grain size, porosity, rotation, emissivity. If the mismatch survives those tests across nights and across instruments, the simple picture bends. Radio can run in parallel. Point a quiet receiver near the hydrogen line and nearby. Record with high resolution and stable clocks. Correct for Doppler drift as the object moves. Look for a tone that persists for minutes and slides exactly as the model predicts. If you do not hear anything, publish. The null. Silence is a result that moves weight back toward ice and rock. Amateurs and professionals can share this playbook. If you work from a backyard or a small campus, cadence is your superpower. Many honest short exposures beat one long trophy. Track in the same way for a whole sequence so the math does not have to fight a moving reference. Use the same comparison stars each night. Publish raw frames with your processed products. Write down exposure times, filters, and whether you tracked the stars or the target. Those habits let other people check your work and stack it with theirs. Large facilities can add fewer but deeper frames. Long slits and integral field units can capture spectra with fine detail. Polarimeters can map subtle order in the light. Coronagraphs can nibble closer to the sun if geometry allows. Spacecraft with the right view can try for opportunistic shots. None of this requires drama. It requires schedules that respect a short window and pipelines ready to share with clear labels. Let us pause and reorient the thread. We began with a blur and a rush of feeling. We turned that rush into checklists that anyone can apply. Now we turn checklists into a plan that carries across many eyes and many nights. The goal is not a single heroic image. The goal is a tapestry of modest measurements that agree. You can help. Reward work that shares methods and data. Share the channels that show their math. Ask for timestamps before you share a striking frame. Every careful click makes the conversation cleaner. If this guide gives you a sense of calm, pass it to one person who loves space as much as you do. There is a reason to hold that calm. The moment the object returns, another headline will compete for your attention. A rock the size of a room slipped past Earth recently closer than our main station's orbit. We spotted it after it left. That shock is not a failure. It is a lesson about what our surveys do well and what they miss. In the next part, we will use that small scare to reset our expectations. It will make us better watchers when the next burst of data on this interstellar visitor lands on our screens. A house-sized rock slipped past Earth closer than our main crewed station, and we noticed after the fact. That sentence feels like a siren. It is also a reality check that makes us better at reading the sky. Tiny objects are the ninjas of near-Earth space. They give little light. They move fast. They hide in the same directions where our cameras fight glare. Surveys do not try to catch every pebble. They hunt the city killers first. A potentially hazardous object is defined as roughly 140 meters or larger and passing within about 7.5 million kilometers of Earth. That is 20 lunar distances. The systems that find those bodies are tuned for dim dots that are still bright enough to register on wide fields at night. They sweep the ecliptic where many targets live. They build lists and return often enough to measure motion. Within that strategy, a rock a few meters across will only appear under kind skies and lucky angles. There is a second reason the little ones sneak by. Warning time shrinks with size. A large object glows gently from far away and grows brighter over weeks. A small one stays invisible until it is near and racing. By the time it is bright enough for an automated pipeline to flag it, the arc across the field can be a dash. If the pass is closest at local daytime, the best ground-based systems are blinded. If the approach is from the direction of the sun, the same problem returns. That is why a close miss after the fact is not proof of failure. It is a reminder that physics and geometry do not care about our comfort. What does this have to do with our interstellar visitor? It reframes patience as wisdom. If we can miss a small rock in our backyard, it is not shocking that we struggle with a faint, fast traveler tens of millions of kilometers away. The answer is not shame. The answer is clarity about priorities. We can hold two thoughts at once. We want the big surveys to keep their eyes on the true threats. We also want flexible follow-up when curiosity objects enter the scene. There is progress that should steady you. Infrared survey, craft in low Earth orbit and in deep space will help with the hard angles. New wide fields with faster readouts will reduce the blind spots created by read noise and smearing. Machine learning can triage streaks that older software threw away as plain trails. Amateurs can add value when they run honest cadences and share raw files. All of these threads pull in the same direction. More light, more often, with better filters for noise. We are taking moments that scare us and turning them into better questions. The missed rock is not a sign that we cannot know. It is a sign that we must use the tools we have with discipline and ask for the tools we still need without drama. There is a psychological wrinkle worth naming. A close pass feels like a horror movie near miss. Your pulse spikes. Your mind drifts to worst cases. Then the feeling fades and normal life resumes. The same cycle can warp how we read the interstellar case. A blurry image feels like negligence. A quiet week feels like a plot. When we zoom out, both feelings soften into understandable limits. Resolution limits, calibration time, survey priorities, daylight and solar glare. Naming these limits is not hand-waving. It is how we keep wonder from turning into suspicion. The small rock also reminds us that the sky is busy. Comets are brightening this month right on cue. They show the textbook behavior that heating predicts. The interstellar object is about to step from glare into view again. That will let us check whether it behaves like those comets once it has faced the same furnace. If it does, the mystery narrows. If it does not, the tests we laid out will guide the next questions. Think of this chapter as a posture, eyes open, shoulders relaxed, questions ready, no panic required. We learned that even close to home we can be surprised. We also learned that surprises become science when we capture them with process rather than with panic. That mindset will serve us in the next chapter as we set the baseline for normal comet behavior. With that picture in hand, we can judge the interstellar visitor by what real ice and dust do under the same Sunday. If we want to judge an interstellar visitor fairly, we need a clean picture of what ordinary comets actually do under the same Sunday. Right now, two bright travelers in our own skies are giving us that baseline. Each is a living lab where sunlight writes the rules in real time. Comets are rubble and ice stitched together by gravity and a little glue. Far from the sun, they sleep. As they fall inward, heat wakes the ice. Solid turns straight to gas. That gas drags dust from the surface and builds a temporary atmosphere called a coma. Seen from Earth, the coma looks like a soft lantern around a sharper core. Push closer to the sun, and the solar wind sculpts the material into tails. A dust tail curves with the object's path. An ion tail points away from the sun almost like a ruler. The tails do not trail behind like smoke from a train. They point where the sun tells them to. Brightness tracks that physics. The simple rule says, as distance to the sun drops, activity rises. But comets are messy bodies. Rotation can swing fresh ice into daylight and cause sudden outbursts. A crust can seal pockets that then vent through narrow jets. When jets spin into and out of view, the light curve can pulse. Photometry captures this as gentle waves and occasional spikes, rather than a smooth ramp. Spectra add the fingerprints. Water usually dominates near the Sunday. Carbon monoxide can drive activity farther out. Carbon-bearing radicals like CN and C2 bloom in the coma as sunlight breaks complex molecules apart. When activity surges, the lines for these species strengthen with the continuum light. When an outburst is dust-heavy and gas-poor, the continuum can jump while lines lag. That is normal too, and tells us about what broke free. Geometry matters as much as chemistry. Phase angle is the angle between the sun, the comet, and us. Near certain angles, tiny dust grains act like mirrors and forward scatter light. The coma brightens in a way that has nothing to do with a sudden change on the surface. Observers correct for this when they compare different nights. If you see a clean jump that survives the phase correction, you can treat it as true activity rather than a trick of viewing. Fragmentation is the dramatic end of the story for many comets. Heat and stress cut the nucleus. Pieces drift apart slowly. Each fragment grows a small coma. The total brightness can wobble as the dust budget redistributes. None of this implies anything unnatural. Ice is weak. Thermal gradients are cruel. A break is as honest as a flare. Non-gravitational nudges are part of the package. When jets push off the surface, they act like tiny thrusters. Over weeks, these pushes add up and shift the path by small but measurable amounts. The key is correlation. When gas production is high, the non-gravitational term rises. When activity fades, the term relaxes. If you graph motion and gas lines together, ordinary comets draw a matching pair of curves. You can already see how this baseline will grade our interstellar case. After perihelion, does the light curve rise and fall with solar distance and phase angle? Do spectra show water and carbon lines growing with brightness? Do small path changes line up with periods of strong venting? Does the coma profile fall off smoothly with radius and only show asymmetries where jets are expected to shape it? If the answers lean yes across different teams, the mystery shrinks toward normal. The two bright comets this month illustrate the range of normal. Each hovers near the threshold of naked eye visibility under dark skies. Each brightens as distance drops, then flickers with rotation and vent geometry. Astrophotographers capture dust fans that widen and narrow. Spectroscopists report expected bands rising in step with total light. Some nights show surprises. A sharp jump likely tied to a weak crust giving way. A sudden fan that fades over days as the jet rotates out of view. The show is lively without being strange. One more honest note. Comets are unpredictable in the short term. A quiet visitor can explode. A showy one can stall. That is why checklists matter more than vibes. When we grade the interstellar object against this living baseline, we will look for the same signatures, not for drama. If it walks and talks like a comet once it clears the sun, the case for ordinary physics grows fast. If it fails the baseline in clean ways, the next tests are waiting. Your eyes are eager allies and dangerous guides. A soft point turns into a shape the instant contrast rises. A ripple of noise arranges itself into a line the moment a sharpened filter bites. The cure is not to stop looking. The cure is to look with rules that keep excitement from drafting conclusions ahead of the light. Begin with scale. A detector decides how much sky one pixel owns. If the nucleus is smaller than a pixel, it cannot show a clean edge. Anything that looks like a blade or a panel near the core is more likely the shape of the optics than the shape of the object. Respect the point spread function. It is the fingerprint of the instrument, and it stamps every bright dot with the same blur. When you compare frames, ask if those apparent edges match the spread you see in nearby stars. Signal to noise sets the outer wall of truth. Stacking raises signal by adding what repeats and lowers noise by averaging what does not. That only works if alignment is honest and drift is modeled. If the target smears, stacking will rescue nothing. Deconvolution can sharpen a soft core, but only inside the bounds that the noise allows. Past that bound, the math starts to invent. The result can look plausible to the eye, which is why we ask for raw frames and not only for processed trophies. Rotation is a simple lie detector. Real structure rotates with the sky or with the body. Instrument artifacts rotate with the camera or stay fixed to the detector. A feature that holds the same angle while the stars turn is likely a quirk of the system. A feature that pivots in step with a measured period deserves more attention. Polarization adds a second check. Random dust scatters light in messy patterns. Aligned surfaces imprint stable vectors that keep their orientation even as brightness flickers. Color can fool or clarify. When only one band shows a crisp edge, while a neighboring band of similar depth shows none, the edge is suspect. When the same line appears across filters with comparable strength, it is more likely to be real. Phase angle can act like a magician. Forward scattering near a special geometry can make a coma look sharper without any change on the surface. Correcting for phase can make a surprise look like a lesson rather than a revelation. Processing choices leave signatures. Sharpening boosts local contrast and draws bright rings around cores. Denoising smooths speckle and can erase faint structures that resist neat curves. Upscalers trained on familiar shapes tend to imagine what they have seen before. Each of these moves can have a place when used with restraint. Each becomes a mask when it replaces measurement with wishful contours. The fix is disclosure. Tell people the kernel and radius. Tell them the denoiser and strength. Let others push the same knobs and see if the feature lives. We are building a shared toolkit so that many eyes can look hard without drifting into stories the pixels never told. This matters because the next burst of data will tempt even careful people to hurry. Haste is expensive when a field is crowded. With eager models and elegant myths, there is a hopeful angle here. The same mathematics that can mislead can also rescue detail honestly when paired with robust priors. Better simulations of dust physics can predict profiles that observers can test. Faster solvers can map parameter spaces that used to take weeks. New computing approaches can compress the time between photons and insight without cutting corners. That is where we are headed next. We will look at engines built for hard problems, how they are crossing important thresholds, and how they will help us decide whether a blur is only a blur or a message that deserves a second look. There is a reason scientists smile when they talk about new computing tools. Better engines change the questions you can ask. In the past year, quantum error correction crossed a practical line. Teams entangled a few dozen logical qubits and kept them alive long enough to matter. Logical means they ride on top of many fragile physical qubits and carry built-in error correction. That stability is the difference between a stunt and a tool. It does not turn the machine into a genie. It turns certain classes of simulations from fantasy into projects. Why should you care if qubits behave for longer? Because some problems explode in complexity when you try to run them on classical machines. Protein dynamics, exotic materials, plasma behavior inside magnetic bottles, turbulence that dances across scales in space and in the lab. Classical codes can approximate these, but they bleed time and require brutal shortcuts. A small quantum register with honest error correction can explore parts of the landscape that would take a supercomputer months. The goal is not to replace classical tools. The goal is to hand them a partner that speaks a different dialect of physics. We already see hints of this partnership. New AI-assisted simulators for proteins have cut timelines for exploring how molecules move and fold. That helps drug discovery. It also hints at what will happen when quantum resources join the loop and handle the parts of the math that carry the most entanglement. The same story appears in materials. When you can model correlated electrons without throwing away the details, you can search for compounds that conduct beautifully or store energy with grace. Fusion research waits in this queue as well. Magnetic confinement is a playground of coupled fields and instabilities. Better solvers mean faster iteration on coil designs and heating schemes. Every week shaved off a design loop moves the first practical reactors closer. Astrophysics will borrow the same engines. Dust dynamics in a cometary coma is messy. Grains interact with sunlight, plasma, and each other across a range of sizes. Radiation pressure pushes in frequency-dependent ways. Gas jets carve patterns that change as the nucleus spins. Classical models juggle all of that but must pick their sacrifices. More compute does not just make pictures prettier. It lets you keep more truth in the equations and still finish before the sky moves on. There is a human rhythm hidden inside this progress. When tools accelerate, the culture of a field shifts. You can test more ideas and kill bad ones faster. You can publish with tighter error bars and fewer caveats. You can afford to run adversarial checks that once felt luxurious. That rhythm protects us from falling in love with the first story that fits. It also means that a public investigation like ours can lean on models that update in weeks instead of seasons. Funding is following the curve. Nations have put billions on the table for quantum infrastructure and for the software ecosystems that make it useful. Big companies publish roadmaps that aim for hundreds of logical qubits later in the decade. Private groups chase photonic schemes, trapped ions, and superconducting circuits. Each approach carries promises and headaches. None is a magic wand. All of them push on the same frontier. Keep coherence, correct errors, scale without losing the plot. The moment a platform can run mid-sized circuits with confidence, whole families of simulations will move from theory to practice. We should pause and reorient the thread that guides us. Our investigation began with images and public frustration. It now touches engines and equations because the fastest path to clarity often runs through better models. When a claim says a coma is too cold for its gas output, you want a code that can juggle grain sizes, porosity, rotation, and emissivity without cheating. When someone says a path change cannot be due to jets, you want a solver that can trace millions of tiny thrusts over weeks and compare them to astrometry. The goal is not to bury wonder under compute. The goal is to give wonder a fair trial. This speed up has a social upside too. It makes transparency easier. If codes finish in hours, teams can share parameter sweeps with the public. Viewers can see how sensitive a result is to assumptions. If a conclusion only lives inside one narrow choice, it will be obvious. If the conclusion holds across a wide range, confidence rises. You do not need to read the source to feel the difference. You will see it in the way uncertainty shrinks and the way disagreements converge. If this kind of progress lights you up, bring someone along for the next step. The same energy shaping models on screens is shaping machines in labs. Reactors are holding star-hot plasmas longer and cleaner. That work matters for energy on Earth and for how far we can go in space. In the next part, we will visit those furnaces, see what changed, and why a few extra minutes at 50 million degrees can alter the future far beyond one mystery in the night sky. In February of this year, a team in France held a star in a bottle for 22 minutes and 17 seconds. The WEST tokamak kept plasma near 50 million degrees while the magnetic cage stayed stable. That beat the previous record. From January at the East machine in China, by more than 4 minutes. Records are not power plants. They are signals that the hard parts are lining up. A tokamak uses magnetic fields to hold a ring of plasma so hot that atoms split and their nuclei can merge. Fusion turns light elements into heavier ones and releases a burst of energy. On Earth, we cannot squeeze plasma with gravity the way the sun does. We use temperature and magnets instead. If the cage holds and the plasma stays calm, the reaction can run for minutes and someday for hours. Twest did not make electricity. It proved that a machine can keep the furnace lit in a steady state for a time that begins to look practical. At the same time, a private player cracked a stubborn piece of engineering. TA Technologies reported they could form and sustain a field-reversed configuration plasma right in the center of their device, using neutral beam injection alone. Earlier designs needed complex formation sections at both ends, and then a high-speed collision in the middle. Removing that hardware simplifies the machine and reduces cost. It also shortens the road to longer and hotter shots. Simpler is not only cheaper. Simpler is more reliable when a system must run day after day. The bench is crowded in the best way. Commonwealth Fusion Systems is building a pilot plant called Spark near Boston, with the first runs planned later in the decade. Helion has completed initial tests on its latest machine that aims for break-even with a different confinement scheme. General Fusion is building a demonstration system that compresses plasma mechanically instead of using a traditional torus. The approaches vary because fusion is a mountain with many routes. We do not know which route will be the highway yet. There is a separate branch that matters for physics. In late 2022, the National Ignition Facility achieved fusion ignition in a pulsed laser experiment. The shot yielded more energy than the lasers delivered to the target. That was a scientific first. It did not mean a laser power plant is ready for the grid. It meant that controlled fusion is not a fantasy. The challenge now is to repeat, to scale, and to turn a pulse into a practical cycle that makes sense outside a lab. Why does this matter for you and for our story? Fusion fuel is made of deuterium and tritium. Deuterium is abundant in seawater. Tritium can be bred from lithium. A fusion plant would produce no carbon emissions. The reaction is self-limiting because the plasma is so thin that any disturbance cools it and the burn stops. The waste problem is smaller than fission. since there is no long-lived chain of heavy elements. The hurdles are real. Neutrons from the reaction pound the walls and make materials brittle and radioactive. Blankets must capture that energy and breed fresh tritium while staying robust. Magnets must hold the cage with grace while the furnace roars inches away. None of these are solved by slogans. They are solved by test loops that now run longer and hotter than ever. Here is the bridge back to exploration. Abundant clean energy on Earth frees budgets and minds. It also points to engines that can change how far and how fast we travel. Fusion propulsion offers very high exhaust velocity and strong specific impulse. That means a ship could carry less propellant to reach the same speed, or reach much higher speeds with similar mass. Travel times to Mars could shrink from months to weeks in optimistic designs. Deep space missions could reach the outer planets on timelines that fit a career rather than a generation. Pause for a quick reorientation. We are not leaving our mystery in the night sky. We are widening the frame that surrounds it. Better tools in labs and in space make future puzzles easier to solve and future trips easier to make. Patience with the present and investment in the engines of understanding pay off together. The point is simple. Bottling the sun is not about a single record or a single company. It is about a series of measured steps that turn astonishing temperatures into routine operations and routine operations into real power. When that happens, telescopes get bigger, missions get bolder, and the hints of life on other worlds move from someday to a plan. Speaking of life, there is a small core in a Martian rock that now carries the strongest suggestion yet of ancient microbes. The data is careful, the language is cautious, the implications are enormous. That is where we go next. A drill on Mars bit into a pale layered rock and pulled out a pencil-long core. Months later, that core began to whisper. The texture looked familiar to geobiologists. The chemistry raised eyebrows. No trumpet blasts, no fossils in silhouette, just patterns that on Earth often trace the slow work of microbes. If that makes your pulse jump, good. Then take a breath. The word that matters most here is potential. The site sits in Jezero crater inside a region called Bright Angel. Billions of years ago, a river spilled into this basin and built a delta. The rock that Perseverance sampled is sedimentary. Fine grains of clay and silt were laid down in still water and then turned to stone. On Earth, those conditions often preserve organic traces. That is why this site was picked years before the rover touched down. In the core, instruments detected organic carbon. They also found sulfur, oxidized iron, and phosphorus. That recipe does not prove life. It does match the chemistry that microbes often leave behind when they chew through organic matter. The showpiece is a set of tiny features that scientists nicknamed leopard spots. These are dots and flecks enriched in iron phosphate and iron sulfide, scattered through the rock like a galaxy of specks. On Earth, similar mineral clusters often form when biology cycles iron and sulfur in muddy sediments. Microbes alter their environment in ways that drive minerals to precipitate right where the colonies live and die. The pattern is suggestive rather than decisive. It is the kind of clue that pulls you to the next test. Alternate stories exist and must be tested hard. Hydrothermal fluids can move through rock and deposit odd mixtures without any help from cells. Impacts can heat and fracture stone and create pathways for chemical gradients that mimic biology. Volcanic gases can interact with brine and lay down patches of sulfur-rich minerals in neat textures. The simple truth is that chemistry alone rarely distinguishes life from lively geology at this distance. That is why the authors use the careful phrase potential biosignature. It is an invitation to ask better questions, not a victory lap. Here is what makes this core special beyond the headlines. Bright Angel is not among the oldest terrains Perseverance has explored. Earlier plans focused on the idea that if Mars ever hosted life, the best time was very early when the planet was warmer and wetter. Finding potential biosignatures in a younger unit stretches the window of habitability. It suggests that ponds and channels may have flickered on later than we thought, or that local warming episodes revived dormant chemistry. Either way, the range of times worth sampling just widened. Perseverance did not simply sniff and move on. It cored the rock, sealed the sample in a titanium tube, and stored it with dozens of others. The sample has a formal name taken from a waterfall in the Grand Canyon. The plan is to bring these tubes home. Only Earth labs can do the isotope measurements and nanoscale imaging that would separate a biological origin from a geochemical look-alike. That return is not simple. Budgets and engineering make timelines wobble. The scientific logic is unchanged. If you want an answer that survives a century of arguments, you bring the rocks to the instruments rather than the other way around. Caution matters here because public hope is high. We have walked this road before. A Martian meteorite in the 90s carried shapes that looked like fossils under a microscope. Later work showed how non-biological processes could create similar forms. That history is not an embarrassment. It is part of how science learns to ask harder questions. The same discipline guides this case. List the features, propose the abiotic routes, design the tests that will prefer one path over the other, then do the work. There is also an emotional truth worth naming. Even a strong maybe on Mars changes how you feel when you look up. It turns a red dot into a place where chemistry tried many tricks and perhaps crossed the thin line into metabolism. That feeling is allowed. It should ride on methods, not on slogans. Let us take a short reorientation of our thread. Our series follows a visitor from deep space and the human drama around it. Life hints in a Martian stone remind us why patience pays. Big answers come from small textures checked with bigger tools. The same ethic will carry us through the last turns of this story, as we zoom from rocks and rivers to the largest questions in the sky. The models that explain galaxies rely on invisible ingredients. New data is testing those assumptions. If some of those ingredients fade, our equations will need a tune. That is where we go next. For a generation, the standard picture of the universe has carried two invisible pillars. Dark matter holds galaxies together and sculpts the cosmic web. Dark energy pushes space to expand faster over time. Together, they account for most of everything. We do not see them directly. We infer them because gravity does not add up without extra mass, and because distant light says space is speeding up. What if those inferences are right? What if they are not? The new data arriving this decade is poking both pillars with sharper sticks. Start with dark matter. Spiral galaxies rotate too fast at their edges if you count only stars and gas. Galaxy clusters bend background light more strongly than visible mass. Allows. These are robust facts. The traditional answer is a sea of non-luminous particles that add gravity without shining. Physicists have built detectors deep underground to catch even a single rare interaction. Those experiments have set strong limits and have not found a clear signal. Every null result narrows the options and pushes the idea towards stranger particles or weaker interactions. Now look at dark energy. When astronomers chart the brightness of standard candles in distant galaxies, they find that the universe began to accelerate a few billion years after the Big Bang. The simplest explanation is a constant energy density of empty space that never changes. Call it the cosmological constant. It is an elegant placeholder. It has also been a source of philosophical heartburn because the measured value is tiny compared to many theoretical expectations. Recent surveys of the large-scale structure now tease a different twist. Some analyses suggest the push of dark energy might evolve over time. If that signal holds, the constant is not constant, and we need a richer story. What would a richer story look like? One path keeps the dark ingredients and lets them change. Dark energy could be a field that rolls slowly. Dark matter could interact a little with itself in ways that smooth out tensions between small and large scales. Another path asks if we have misplaced our trust in fixed laws. Perhaps gravity or other constants drift slowly as the universe ages. If the strength of gravity, or the effective link between matter and geometry evolves, some of the signals we attribute to dark stuff could be mirages created by using the wrong ruler. Modified gravity ideas have a long history. Some versions can match galaxy rotation curves without dark halos by changing how acceleration works at very low levels. These successes often stumble on galaxy clusters or on the detailed pattern in the cosmic microwave background. Newer proposals try to bridge those gaps by making the modification depend on environment or time. The promise is to explain many effects with fewer invisible entities. The price is complexity and a need to pass a gauntlet of tests across many scales at once. Here is the discipline that keeps this debate honest. Any challenger must hit the same targets that the standard model already hits. Lensing maps, cluster counts, supernova distances. The way galaxies clump as a function of scale, the smoothness of the microwave background and its tiny ripples, the late-time push of cosmic acceleration. If a new rule matches 1 but breaks 3, it is not an advance. If a new ingredient fits 2 but adds 3 free parameters, it may be beauty on paper and trouble in practice. The scoreboard is not opinion. It is a list of independent datasets that stubbornly demand to be fit together. We began with a blur around an interstellar visitor and learned to separate frustration from physics. Now, we are looking at a blur in our cosmic map and applying the same ethic. Curiosity invites bold ideas. Measurement is the brake that keeps them from running past the guardrail. What would it mean for our investigation if the cosmic rules are a little off? If gravity behaves differently at very low accelerations, then the way dust and gas move in a coma could carry subtle fingerprints we do not expect. If constants drift slowly, then thermal and chemical balances through the history of planetary systems might look different than our favorite models predict. The link is not direct. It is a reminder that every specific puzzle lives inside a larger set of assumptions. When the large set shifts, interpretations closer to home can shift as well. The next few years will be decisive. A giant survey camera is scheduled to begin scanning the sky night after night and will map billions of galaxies with exquisite detail. Space telescopes will add clean measurements of distances and lensing on very large scales. If dark energy evolves, those data will reveal its tempo. If dark matter is a particle in the friendly mass range, a new crop of detectors might finally see it. If neither appears where expected, the pressure to adjust the rules will rise. There is a practical promise inside this grand argument. As the global community sharpens models to fit sky-wide data, the same tools flow back to niche investigations like our interstellar case. Better lensing pipelines teach us how to track faint light honestly. Better time series analysis honed on billions of galaxies teaches us how to read subtle variations in comet brightness without fooling ourselves. The cosmos is a school that trains you while it tries to confuse you. So, do we need dark stuff or new rules? The honest answer, right now, is that the standard model remains a powerful fit to an enormous body of evidence, yet it creaks at the edges where new data press. Either path forward will demand transparent predictions and public wagers. That is good news. It means we will not argue forever. We will measure until the scoreboard shows a winner. Next, we bring the view back down from the cosmic map to the launch pad. As our tools improve and costs fall, access to space is changing from rare spectacle to regular work. That cadence shapes how quickly puzzles like this one get solved. It also shapes who gets to take part. The future of this investigation depends as much on rockets and ride shares as it does on equations. Not long ago, a rocket launch felt like a national holiday. Today, it can feel like a Tuesday. Reusability has turned spectacle into service. Boosters land, get refueled, and fly again. Small launchers share the market with heavy lifters. Tourist flights lift for minutes of microgravity, while cargo ships refill stations with quiet efficiency. When cadence rises, curiosity rides more often. That cadence matters for science. Frequent launches mean you can send specialized instruments instead of waiting years for a single do-everything payload. Rideshare slots let small teams fly, compact telescopes and sensors that would never have made the cut in an older era. If an unexpected visitor appears, a rapid response mission is no longer a fantasy. It becomes a queue management problem. That is still hard. It is far less impossible than it was. Programs across the world are building the ladder higher. A giant stainless steel vehicle in Texas is learning to leave and return as a system. NASA is assembling a lunar campaign that will test surface operations and logistics. Europe is investing in new launchers and robotic exploration. China operates a modular station and aims for a base on the moon. India stacks mission wins that expand capability step by step. Japan pairs precision robotics with ambitious plans for cislunar work. Competition and cooperation pull in the same direction. More lift, more often, for more kinds of missions. As access normalizes, instruments change too. Telescopes that would have been one-off monuments become constellations of small nodes that work together. A group of compact infrared eyes can watch near the sun and fill gaps in ground surveys. Swarms can map the sky for brief flashes and streaks with coverage that a single giant mirror cannot match. If a new object appears and crosses behind the sun, some of those eyes can still watch from different lines of sight. That is how cadence converts into resilience. There is a human shift inside this cadence. Space stops being priestly. It becomes a workplace. Technicians and students touch flight hardware as part of ordinary training. University teams build CubeSats that answer narrow questions and feed data into public archives. When more people take part, the number of honest checks rises, mistakes surface faster, myths starve sooner. The conversation about risk and reward becomes broader and less brittle. We should keep our feet on the ground even as the launch rate climbs. Access does not erase the hard parts. Radiation still gnaws at electronics. Thermal cycles still crack structures. Propellant still leaks. Budgets still decide who gets to fly and who must wait. The point is not to romanticize volume for its own sake. The point is that routine reduces the cost of error and the cost of trying again. That freedom to iterate is how you learn quickly without falling in love with the first answer that arrives. Let us pause and reorient our thread. We began with a blur that felt like a door closing. We crossed through patient math, careful checklists, and long pipelines. Now we stand in a world where rides to orbit are frequent enough that a new plan can be more than a press release. That world is where puzzles shrink faster because attempts are cheaper. All of this loops back to the object that pulled us into the story. Within days it will step from behind the sun and show its hand. The next frames and spectra will either settle nerves or raise the stakes. Either way, the future you just heard about will decide how quickly we can respond. If it is ordinary, cadence will let us collect and catalogue and move on with grace. If it is not, cadence will let us listen, measure, and act without delay. We have arrived at the edge of the fork. The last chapter lays out the two paths with clarity and poise. It explains what each outcome will mean for science, for institutions, and for you. Then it leaves you with a shared promise. Whatever the sky says, we will keep the signal clean. The curtain is about to rise. When the object steps out from the sun, there are really only two roads. On the first road, it behaves like a comet. The light curve climbs with solar input and phase angle, then softens. Spectra show water and carbon lines that grow and fade in step with brightness. Small path nudges match periods of strong venting. The coma profile falls smoothly with radius. Polarization looks messy and natural. Infrared power balances the energy needed to make the gas we see. Radio stays quiet. In that case, the story is not a letdown. It is a lesson. A rare interstellar visitor passed through our house and followed the same rules that govern every dusty snowball that dared to dive toward the Sunday. We learned how hard it is to see structure below a pixel. We learned why quick looks can mislead. We learned what patience buys. On the second road, the object refuses the script. Astrometry shows a clean impulse that cannot be tied to gas jets. Thermal data stays cold while mass loss climbs, even after every ordinary knob has been turned through its full range. The coma holds a subtle geometry that persists across instruments and rotates with the body rather than with any camera. Polarization maps show stable vectors that keep an attitude. A narrow tone near the hydrogen line appears, drifts with Doppler as predicted, and is heard by more than one dish. None of these on their own would close the case. Together, they would force us to admit that nature has written a different kind of page, not proof of intentions, not a plot, clear signals that the object is not only ice and dust. Most outcomes will live between those poles. That is fine. Science grows in gradients. If the results point to ordinary, we mark a win for method. We will still ask the high-resolution teams for their calibrated frames. We will still fold the measurements into models that will improve the next chase. We will still keep a watch on future interstellar arrivals with better pipelines, clear expectations, and a public that knows why a dot can be honest. If the results lean toward extraordinary, our checklists become the scaffolding for the next phase. More listening, more precise astrometry, more careful polarization. If agencies hold data, we ask for schedules and metadata rather than slogans. If rumors flare, we answer with files and plots. We keep the temperature low and the standards high. Either way, there is a responsibility that does not change. Treat uncertainty like a shared asset. It is not a weakness to say we do not know. It is a strength to show exactly what would change our minds. That is how we keep trust when the sky is silent and when it shouts. That is how we keep wonder from being eaten by noise. There is also a personal stake here. For months you have carried this mystery through feeds and late-night debates. You watched a blur become a battleground. You watched numbers calm a panic. You watched a community split and then slowly agree on how to test. If that journey gave you a steadier way to look at the world, keep it. Use it on the next headline. Use it on the next claim that seems too neat to be true. Curiosity with discipline is a habit that repays every hour you invest. If this series helped you breathe through the drama, share it with someone who loves space and good arguments. Tell them that the sky is not a circus trick. It is a laboratory that belongs to all of us. If you want to ride with us as the first post-perihelion frames land, tap the button that keeps these investigations in your feed. Your attention tells the platforms that careful work matters. Before we leave, hold the larger picture in your mind. Fusion furnaces are staying lit longer. Quantum tools are learning to keep their balance. Rides to orbit are becoming routine. Rovers are tasting rocks that might hold whispers of ancient cells. Surveys are about to map the sky with a patience no human could sustain. Each of those threads makes the next mystery easier to untangle. Each of them makes the world a bit more honest because they convert awe into measurement and measurement into understanding. Here is our promise. We will keep the signal clean. When the images and spectra arrive, we will grade them against the yardsticks we built together. If the object is ordinary, we will say so with gratitude and close the case with pride in the process. If the object bends the rules, we will show you exactly where and how, and we will invite the whole community to push on the result. No breathless shortcuts, no performative doubt, only the stubborn joy of finding out what is true. Look up. The sun is bright, the glare is fading, and a traveler is about to speak in light. Whatever it says, we will listen with the calm courage that comes from knowing how to ask the right questions and how to wait for honest answers. Thank you for walking this road with me. Stay curious, stay kind, stay ready.